Entropy always increases. That's the second law of thermodynamics. And it's the strangest, most profound, most philosophically troubling law in all of physics. Not because it's complicated. The statement is simple. In any closed system, entropy, a measure of disorder, never decreases. It either stays the same or goes up. That's it. That's the law. But the implications are staggering. The second law is why time has a direction, why you age but never get younger, why eggs break but don't spontaneously reassemble, why the universe started in a highly ordered state and is sliding inexorably toward maximum disorder, why heat flows from hot to cold and never the reverse, why you can turn work into heat easily, but turning heat into work is hard and always wasteful. The second law is the only fundamental law of physics that distinguishes past from future. Every other law, Newton's laws, Maxwell's equations, Einstein's general relativity, even the Schrödinger equation works the same forward and backward in time. Run any process in reverse, and you get another valid physical process, but not thermodynamics. Entropy increase has a direction, and that direction defines the arrow of time. I'm Leonard Susskind. I've spent 50 years thinking about entropy, about statistical mechanics, about how the microscopic laws of physics, which are time reversible, give rise to macroscopic irreversibility. And the more I understand it, the stranger it becomes. Let me show you why. Start with what entropy actually is, because most people have only a vague sense of it as disorder or randomness. That's not wrong, but it's not precise enough. Entropy is a measure of the number of microscopic states that correspond to the same macroscopic state. Let me make that concrete. Imagine a box of gas. At the macroscopic level, you can describe it with a few numbers: pressure, temperature, volume. But microscopically, the gas is made of billions of molecules, each with a position and a velocity. There are an astronomical number of ways to arrange those molecules that all give the same macroscopic pressure and temperature. Entropy measures how many such arrangements there are. More precisely, entropy S is proportional to the logarithm of the number of microstates. S equals K log W, where W is the number of microstates and K is Boltzmann's constant. This is the Boltzmann formula. It's engraved on Boltzmann's tombstone because it's one of the most important equations in physics. Now here's the key insight. Most configurations of molecules correspond to high entropy. Very few configurations correspond to low entropy. If you have all the gas molecules huddled in one corner of the box, that's low entropy. There are very few arrangements of molecules that all happen to be in one corner. If the molecules are spread evenly throughout the box, that's high entropy. There are vastly more arrangements where molecules are distributed roughly uniformly. So if you start with gas in one corner and let it evolve, it will spread out. Not because there's a force pushing it, but because there are more ways for the molecules to be spread out than to be concentrated. The system explores the available states randomly, and since most states correspond to high entropy, it ends up in a high entropy state. This is why entropy increases, not because of a fundamental law that forces it to, but because high entropy states vastly outnumber low entropy states. It's statistics, not dynamics. But here's the problem. The fundamental laws governing the molecules are time reversible. If you film molecules bouncing around and play the film backward, the reversed motion obeys the same laws as the forward motion. Every collision, every interaction works equally well in reverse. So why doesn't entropy decrease? If the laws are time reversible, why don't we ever see the gas spontaneously gather itself into one corner? The answer is, we could. It's not impossible, it's just stupendously improbable. If you wait long enough, and I mean long enough that the wait time dwarfs the current age of the universe by factors you can't even write down, random fluctuations will eventually put all the molecules back in the corner. It will happen, but the probability is so low that it will never happen in practice. Not in the lifetime of the universe. Not in 1,000,000,000,000 lifetimes of the universe. This is the statistical nature of the second law. It's not an absolute law like conservation of energy. It's a probabilistic statement. Entropy almost always increases. Not always, almost always. But almost always is so close to always that for any practical purpose, it's the same thing. Now let me tell you why this is philosophically disturbing. The laws of physics are time symmetric, but the universe has a time asymmetric arrow. Entropy increases toward the future. We remember the past, but not the future. Causes precede effects. All of these are consequences of entropy increase. But entropy increase is not a fundamental law. It's an emergent statistical regularity, which means the arrow of time is not fundamental. It's an accident of initial conditions. Let me explain what I mean. If you have a box of gas in a high entropy state, molecules spread evenly, and you run the clock backward, you still see entropy increasing. Wait long enough going backward in time, and you'll see the molecules spontaneously gather in a corner. From that point, running the clock forward again, entropy increases as the gas spreads out. So entropy increases both toward the future and toward the past from any local entropy minimum. The direction of entropy increase is not a property of the laws. It's a property of the boundary conditions. It's a consequence of where you start. The universe started in a very low entropy state. The Big Bang was not a maximum entropy random mess. It was highly ordered, nearly uniform density, very low gravitational entropy, and from that low entropy initial condition, the second law has been operating ever since. Entropy has been increasing for 13.8 billion years. But why did the universe start in a low entropy state? Nobody knows. This is called the past hypothesis, and it's one of the deepest unsolved problems in cosmology. If the Big Bang were a generic initial condition, if the early universe were in a maximum entropy state, then entropy couldn't increase. It would already be at maximum. There would be no arrow of time. No structure formation, no galaxies, stars, planets, life, just equilibrium. Boring, featureless equilibrium. The fact that we exist, that there's complexity, that there's an arrow of time, all of this depends on the universe starting in a special low entropy state. And we don't know why. Now let me tell you about Maxwell's demon, because this is where the second law gets even stranger. In 1867, James Clerk Maxwell proposed a thought experiment. Imagine a box of gas divided in half by a wall with a small door. A demon sits at the door. When a fast molecule approaches from the left, the demon opens the door and lets it through to the right. When a slow molecule approaches from the left, the demon keeps the door closed. When a slow molecule approaches from the right, the demon lets it through to the left. Over time, the demon sorts molecules, fast ones on the right, slow ones on the left. The right side gets hotter, the left side gets cooler. Entropy decreases. The demon has violated the second law. This paradox bothered physicists for a century. How can the second law be fundamental if a demon can violate it? The resolution came in the 1960s and was fully worked out by Rolf Landauer and Charles Bennett. The demon must record which molecules it's letting through. It must store information about the molecule's speeds. That information storage has an entropy cost. When the demon erases its memory to make room for more observations, it must dissipate heat, increasing entropy elsewhere by at least as much as it decreased entropy in the gas. The second law survives. But the price is profound. Information is physical. Information has entropy. Erasing information generates heat. You cannot reduce entropy without increasing it somewhere else. The second law applies not just to matter and energy, but to information itself. This connects to computation. Every irreversible computation, every operation where you erase bits, where you lose information, dissipates heat. There's a minimum energy cost to erasing one bit of information, kT ln 2, where K is Boltzmann's constant and T is temperature. This is the Landauer limit. Modern computers dissipate far more than this because they're inefficient, but even a perfect computer must dissipate at least this much energy for every bit erased. Information and thermodynamics are fundamentally connected. Entropy is not just about energy spreading out. It's about information being lost, about the macroscopic state becoming compatible with more and more microscopic states, about the future becoming less determined by the past. Now let me tell you about black holes, because this is where thermodynamics becomes truly strange. In the 1970s, Jacob Bekenstein proposed that black holes have entropy, not metaphorical entropy, real thermodynamic entropy proportional to the area of the event horizon. Stephen Hawking extended this, showing that black holes radiate and have a temperature. A black hole is the ultimate entropy reservoir. Throw anything into a black hole, a book, a computer, a low entropy system, and it increases the black hole's entropy. The black hole encodes that entropy on its horizon. And since the second law still holds, the black hole's entropy plus the entropy of everything outside must increase. This led to the generalized second law. The entropy of matter outside black holes plus the entropy of black hole horizons never decreases. This is a modification of the traditional second law to account for the existence of black holes, and it's been central to understanding the information paradox and the holographic principle. Black holes are thermodynamic objects. They have temperature and entropy. They're subject to the laws of thermodynamics. And this suggests something profound. Thermodynamics is not just about molecules bouncing around. It's a fundamental feature of space-time, of gravity, of the universe at the deepest level. Now, let me address something that troubles people. If entropy always increases, the universe is doomed. Eventually, all usable energy will be converted to heat, all temperature differences will equalize, stars will burn out, black holes will evaporate, and the universe will reach thermodynamic equilibrium, maximum entropy, uniform temperature, no structure, no complexity, no life. Just a thin gas of particles and radiation spreading through an ever-expanding void. This is called heat death. And yes, it's the ultimate fate of the universe if current cosmology is correct. Trillions of years from now, long after the last star has died, long after the last black hole has evaporated, the universe will be cold, dark, and dead. Maximum entropy. No more interesting processes, no more change. The second law is a one-way street, and the street leads to heat death. But here's something subtle. While entropy increases globally, it can decrease locally. You are a low entropy structure. You maintain your organization by consuming low entropy food and excreting high entropy waste. You decrease your own entropy by increasing the entropy of your surroundings. Life is a local entropy decrease powered by a larger entropy increase elsewhere. The same is true for any organized structure. Galaxies form, stars ignite, planets coalesce, all local decreases in entropy, all powered by gravitational collapse, which increases entropy overall. The universe can build complex structures as long as it increases entropy somewhere else in the process. This is why the second law doesn't forbid complexity. It just says complexity is temporary, local, and transient, bought with entropy increases elsewhere. And eventually, when the universe reaches maximum entropy, complexity will be impossible. No more pockets of low entropy to exploit, no more free energy to organize structure, just equilibrium. Now, let me tell you about something that deeply bothers me. The second law is the only law of physics that's not fundamental in the usual sense. Every other conservation law, conservation of energy, conservation of momentum, conservation of charge, follows from symmetries. Energy is conserved because the laws of physics don't change with time. Momentum is conserved because the laws don't change with position. These are deep, fundamental symmetries encoded in the structure of the universe. But entropy increase, it's statistical, it's emergent, it follows from the large number of particles and the random nature of their interactions. It's not a symmetry. It's not a conservation law. It's a probabilistic tendency, and yet it's the most powerful constraint we have. You can violate energy conservation in quantum mechanics briefly via the uncertainty principle. You can have virtual particles that borrow energy from the vacuum for fleeting moments, but you can never violate the second law, even briefly. Entropy increases always without exception in every closed system at every scale. A statistical law is more absolute than the fundamental conservation laws. That's bizarre. Here's another strange thing. The second law is the only reason we have memory. Memory requires recording information. Recording information requires a physical change, flipping a bit, magnetizing a domain, forming a synapse. That change increases entropy. You cannot remember without increasing entropy. Memory has a thermodynamic cost, and memory is directional. You remember the past, not the future. Why? Because the past was lower entropy than the present. Records from the past survived because they were stable configurations that persisted as entropy increased. But there are no records from the future because the future hasn't happened yet. The future is higher entropy, less determined, unknowable. The arrow of time, the direction from past to future, is the direction of entropy increase. And that's the only reason you experience time as flowing in one direction. Without entropy increase, there would be no subjective sense of time passing, no memory, no causality, no distinction between before and after. Let me end with a deep question. Why does the second law hold? The standard answer: because the universe started in a low entropy state. High entropy states outnumber low entropy states. From a low entropy start, evolution toward higher entropy is overwhelmingly probable. The second law is statistics plus initial conditions. But this just pushes the question back. Why did the universe start in a low entropy state? Why wasn't the Big Bang a maximum entropy explosion? Why was there order to begin with? Some cosmologists propose that the Big Bang wasn't the beginning, that it was a transition from a previous state, that the multiverse as a whole might be in equilibrium, with our universe being a rare low entropy fluctuation. But this is speculative. We don't know. What we do know is this: the second law is real. Entropy increases. Time has a direction. And that direction is the only reason we exist, the only reason there's structure, complexity, life. The universe is running down, and eventually it will reach equilibrium. But until then, we have time, we have complexity, we have structure, we have life. All of it temporary, all of it local, all of it bought with entropy increases elsewhere. The second law is the strangest law in physics because it's not a law in the usual sense. It's an emergent consequence of statistics and initial conditions. And yet it's the most powerful, most inviolable, most philosophically significant principle we have. It defines the arrow of time. It explains irreversibility. It predicts the ultimate fate of the universe. Entropy always increases. And that simple fact is both the most obvious thing about the world and the deepest mystery we've encountered.